Yes, welcome back everyone. Let's restart the game physics lecture. We've actually come to the last chapter, aptly called completing the picture. So we'll actually get back to rigid body simulations a bit within this chapter and then look at different topics that were actually not fully completed in the previous rigid body lectures. The larger goal here is to move towards more of an actual engine that you would find in a game or so. And as you'll see, there are a few extensions and tweaks, and also somewhat related to that, I want to later on highlight one simulation algorithm that aims for more complex interactions and effects. All right, so the first topic in this part actually will be contact and friction. Then we'll also talk about correction algorithms. More on that later. These actually go towards this full rigid body algorithm that puts the pieces together. And then we have the more advanced simulation algorithms in the context of cloth simulations. Yeah, so first, contact and friction. We often have the case that objects are in contact. So here you can nicely see the background. For example, I have on the table here lots of objects stacked on the table that don't move, right? They're resting. In reality, this is a super easy and trivial situation. Here's a mock-up of that in a simulation. We have a box resting on this brown ground plane. And now, turns out, despite being super easy and obvious in reality, it's not that easy in a simulation. So what do we have in such a case? Well, we still actually need to achieve a complete balance of acting forces. Right, a block like this, or my books are resting, they're not moving at all. However, they are, for example, experiencing gravity. There is a lot happening. They are potentially complex objects with internal structure, and they are being constantly accelerated. However, the gravity, especially as one of the examples, actually needs to be perfectly cancelled out by the supporting ground. In this case, the ground floor or a table or any surface the object rests on. So yeah, we actually do have a acceleration and also hence a push off the object resting on another one. And right, we need this cancelling out due to, in this case, this resting contact in order to achieve that the object really does not move. As you can imagine, in a computer, that really means we need to perfectly even this out. If we have slight inaccuracies over time, right, so if we don't integrate this accurately enough, then we might over time suddenly see weird motions of our object that are probably quite disturbing and really should not be there. In this case, it's very obvious, right? We have our one object, it's being pushed down, the blue arrow, and it needs to be counteracted in some way by a response. In this case, we basically just need to flip the blue arrow, right? It's quite obvious. However, it easily becomes more complicated. So here, it's still a very simple situation. It's just three boxes resting on the floor. But now the situation is already a fair bit more complicated. We now have this top box resting on the other two, and they're a bit shifted. So in the middle here, right, the mass of this object is actually being transferred to the other two over these surfaces where they rest on each other, and hence the force applied by these two objects onto the ground plane now is actually uneven. And as you can imagine, from this object resting in the middle, right, this is pushing down here and kind of pushing these objects down at the edges. At these vertices is actually larger, and potentially we actually have a whole pressure distribution that extends from a larger one here all the way to a somewhat lower one on the left-hand side here, right? So the weight of that object is distributed through the geometry and configuration of these objects onto the resting contract with the floor. And now, if we imagine that this is all at rest, the forces exerted by the ground floor here actually need to also counteract all these more unevenly distributed forces. And yeah, if we extend this, you can imagine stacks of objects to any height where we actually would need to look quite far in order to really resolve what's happening at the ground level. Right? Basically, we need to really find out, based on this lowest surface, what kind of objects are in what configuration and with which masses resting on each other, producing some effect here on the ground plane. And yeah, if we have more of them, it's really not enough to just look at, say, one object in pairs or so. We really need the whole chain from one object all the way through all interactions of these objects. Right, so even in this still fairly simple case, it's actually not enough to look at pairs of objects. That will not look far enough. Yeah, the general idea here is that instead of looking at object A and B, one collision point and an instantaneous reaction from the bodies, for more generic and more realistic real-world settings, we actually need to look at larger numbers of impulses. So right here at the bottom now, I've picked, for example, one of the objects from the previous slide with multiple contact points, or just to give some example. It's probably not from the previous slide looking at it. But let's imagine that we're looking at this object and this is now colliding with others at different points and basically experiencing an influence from multiple other rigid bodies around it. So if we now look at the setting here, we can actually still reuse our impulse formulation. So if we look at one specific final impulse, so one change of a velocity due to an impulse, here for an object I, so this is now, right, we could say this is our object I here, then, right, I do have, oh, sorry, not yet. Right. Then what we now can do here actually is we can keep our impulse formulation and introduce a loop, in this case over k, for our object I that accumulates the influence of the impulse. So a bit similar to forces, the impulses we can accumulate with addition. So that's in a way still fine and relatively simple. This is really just adding up these k impulses that we have now. So right here we could have k equal to 3, and they're all different impulses, so they could have a different magnitude acting on linear and angular part as before, but they're actually all acting along the normal direction of the body I now. So mind you, this is the normal of the body I. It can of course have different values on different sides of the body, but all with respect to one of the objects. Right. And yeah, we can pull that together into one loop here, and as before, pull in the normal of the ith object to basically resolve these impulses like before at their individual collision points. So here in this equation we also have the individual locations of where the impulse is acting. Right, so these actually now are varying for all the k impulses that are being computed. Right, so nonetheless, it looks a bit non-trivial at first, but in a way we are just summing up the contribution from multiple impulses now. The key idea is that, in a way, no matter how many of these impulses we have, what needs to hold in the end is that once we apply the impulses, we need to fulfill this condition that we had. Namely, that the relative velocity, or all the relative velocities that we had, they need to be separating in the end. And this is now a bit of a tricky part. It also sounds quite obvious at first, but if you think about it, even if I have one object and I'm applying an impulse, it's easy to fix the relative velocity in just that point. As soon as I apply an impulse in another point, I actually will receive some reaction within my body, and this might change what's happening in the previous point. So because of the rigidity, right, the object is not deforming in any way. All changes I do anywhere of the body potentially influence all other points by rotational velocity, while the translating one, and hence they can invalidate and destroy that property that I computed for, say, a given pair previously. And this is now what we need to pay attention to. And right, this is essentially what this equation up here should specify, that even if I just look at the velocity change in one point, so I think this is actually a better way to put it. We can say this down here, this is one of the velocity changes we're looking at, velocity change I. This is actually influenced by all of the k impulses being applied all over the rigid body. They all influence the final velocity we see at that one point on our object. And hence, as a consequence, this means we cannot just look at this one side in isolation anymore, because all the other updates we might do in other parts of the body influence our solution here. Yeah, so in a way, this is not a fundamental problem. Right now we have multiple equations. As mentioned before, we can write out all of these. They all need to fulfill the inequality for the relative velocity that we had at the end. However, on the one hand, it actually means we cannot just evaluate it. We need to solve the system of equations together. And it turns out, because of the inequalities, there is actually no unique solution. The inequality turns out to be a very important component here. If we would say that the relative velocity plus the impulse is equal to 0, then it would actually be easier to solve here. But that would mean that all the relative velocities after applying the impulses are actually zero, which means all the points where bodies collided stick together. That's called the glue effect. And in practice, that actually looks quite unrealistic and ugly, because it means that any object that comes together and collides, instead of bouncing away, they don't go into each other, but they stick together and move on, which is clearly not what happens in reality. Rather, we want the impulses to be as small as possible, right, to, in a way, minimize the energy of the impulses. And hence we really have to respect the inequalities and not just enforce the relative velocities as zero. And turns out in this case we actually need a so-called LCP solver, because this is a quadratic programming problem, as it's called. There is also its own kind of group of solvers to work on these problems. The simplest one is actually what's called a Gauss-Seidel step. These Jacobi or Gauss-Seidel iterations typically mean that we pick individual equations, compute solutions for them, and update our current state, and then keep on doing that for the different equations that we have. So in this case, that could mean we resolve one impulse, apply it, but then we might actually have caused some trouble in another one of them. We pick the next one, apply it, well, then the first one might be invalidated, but we just keep on going and iteratively come back to the first one, continue with the second one, until hopefully on average we have actually found a solution that that satisfies all of them. So as you can imagine, this kind of iteration and repeated evaluation can be slow, but you can actually show that this equation-wise update will converge to a solution. If you're interested in faster converging, better LCP solvers, there's a nice SIGGRAPH course on these rigid body simulations. Yeah, so just as an outlook, but as you can imagine, this would be a nice extension or so for a project, but this goes a bit beyond what we can easily do here in the lecture. Fundamentally, it's still just working with the impulse equations like we had them before. Yeah, one thing pointing out here that are worth noting is that this system matrix that we get in this case actually kind of gives us a graph. It basically encodes the graph of influences in our system, so between the objects. And I have a small example here that you can already see. So here we have different objects, A being the ground floor, and the collision points, the estimated ones, are highlighted here in orange. And now if we look at this graph, we basically start from the ground floor. Many of the objects are related to it. Then we actually have two contact points here for object B. And, sorry, we're starting with H. Sorry, here, H. Two contact points. And here are the ones for B. Now, for B, we're already done, right? There's nothing on top of B. But now for H, our graph continues. So here we have G, and then it also goes to F. H also touches F, and both of them in this case touch E. Nothing above E or beyond, so this is actually the end now. But we have another small cluster here of C and D. And if we now set up this LCP problem, then we'll actually get a big matrix where we have data, impulses, in a long vector for all our objects, A to H. So actually we'll have one entry here for each one of these collision points, right? For every pair, we need to solve the impulse. And then in our matrix now, right, for example, for certain part A, we would get a certain equation in here for H maybe that encodes a certain influence between these two objects. I don't want to write out this matrix that would now contain these impulse equations, but you can imagine that this graph, the connectivity between the objects, actually is contained in this matrix structure. Yeah, another alternative called micro collisions is actually as advertised in the Millington book that I recommended earlier. And here the idea is that we actually treat these resting contacts as a series of small collisions happening to the object. And in a way, the key insight here is that we know from our setup what's causing the problem. So this is a bit specialized, but knowing that we have a kind of global accelerating force like gravity, we know that in each time step what's causing the problem is actually this acceleration by time step times gravity. Right, that's really added every time again, and that's what we like to cancel out. So we actually need effectively we need this counterforce of the same magnitude, which also now, well, if we would just compute a normal collision, we would actually get additionally a bounce back depending on the coefficient of restitution and the previous velocity of the object, right? It might not have yet fully come to rest. It might have had some residual small motion happening. Yeah, so we know that this is what would be caused by this acceleration, and knowing what it is, we can now for collisions that we identify or kind of flag as resting, we can directly remove that from the impulse. So from the bounce back in our impulse formulation, we can directly subtract this part of the response. Note that this change actually in reality never happens, because in reality we never have these time steps of a larger size. Reality is continuous. The objects constantly push against each other. It's really from making this larger jump in time forward that we suddenly see this acceleration of time step times gravity and these weird potential the jumpiness of the rigid bodies. Yeah, so right, we can actually really remove this gravity acceleration, and additional tricks to make the bodies rest would be to also detect very small velocities, and in this case is possibly decrease the coefficient of restitution to make sure that they don't bounce back. Yeah, so let me quickly write out here on the slides what that looks like if we actually remove the gravity bounce back. So previously in the fraction for our impulse, we had this term on the top of -1 plus c times relative velocity, right? I hope you remember. And what we changed that to is the following expression. This one it might look slightly unreliable. Sorry, it is very reliable. That might look slightly unintuitive, but this comes from the fact that we actually do need the full 1 here. So this we don't want to change. Hence, we're keeping basically the relative velocity being multiplied in here. And then from the remainder, from c times the relative velocity, here we now subtract the velocity change. Here it's called this delta V last. This would amount to, for example, time step times gravity. And also because we're typically evaluating this impulse not necessarily along the ground, but some other direction as well, only the component that was actually working along the direction that we're considering for the impulse. Right. So right, this is a term that actually removes this bounce back from gravity. Yeah. Additionally, right, if we want to reduce C, that's relatively straightforward. Right, we can check for the for small velocities and then set Z closer to 0 in order to prevent that objects actually bounce away from each other. So to come to a small summary for the contact part here, if we treat these collisions like we did so far sequentially, then we would actually get a lot of small impulses per time step, and an alternative would be, and actually potentially the best solution would be really to treat all our rigid bodies in our simulated world as a coupled system of objects and solve the equations together with these LCP solvers. As a workaround, we can iterate or basically remove the bounce back from gravity directly. Yeah, and with that I want to come to a slightly different topic that we also neglected so far, namely friction. And this is right a very well-known fact, as I'm sure you all know. So now let me try to improvise and show this here. I'm sure you all know this famous experiment where we have some object on an inclined plane. You can see it here. Right, it's at rest, and then as we start tilting this plane for a while, even though it's still at rest, it is inclined. The object does not start moving, right? And then as I go steeper and steeper, at some point the friction force will not be large enough and my object will start moving. And for now this is still stable. So this is actually a fairly good one. Oh. Now it was too much. This is a well-known effect that we know happens in nature, and it's actually also an interesting one to include in our simulations. So for that we need some extensions. We have not dealt with this at all. And first let me explain the kind of more accurate, more generic force view, and then a bit like with impulses before, we actually want to move away from the force viewpoint and treat it differently by changing the impulse again. But first the what really happens in terms of forces. So for that we need to decompose this pushback of the object on the inclined plane, and we need to consider the normal part, so the one along the surface, and the tangential part along for movements along the surface. And we actually need to distinguish two types of friction. So there's static friction that I just demonstrated, which actually really keeps the objects from moving, and it was growing as I inclined the plane because we have more and more inclination and reason for the object, for the little box, to actually start moving down. And at some point it will actually not be enough and the object will start moving. But here if we now look at this little box on the plane, due to its gravity there's an overall force pushing down, and this we can now decompose into the normal direction and some tangential part. You can imagine, as due to gravity being fixed in terms of direction, we will always see a larger and larger tangential part if I increase the inclination of the plane. And in reality, this is actually right. There are material parameters here. This is not so easy to determine for surfaces, but it really depends on the roughness of the surface, so how much the microstructures of the surfaces interlock to give us this friction effect. But in general, yeah, we can actually typically approximate it with a single parameter mu here, mu static for the static part. And here now we have this inequality that there's basically this factor that limits the amount of static friction that I get along the normal direction. And then you can imagine if the inclination is too big and I have too much of a pull along the surface, then this will actually not be enough to cancel out the movement. And then as soon as it starts moving, as soon as it starts going down the slope, typically the actual force being applied from friction reduces, because now the surfaces don't interlock as well. We have a motion, a shifting along each other, and then the friction force actually typically is much smaller than the static part from before. So here I have the equations on the slides. The dynamic part first, maybe. Here we have another factor, the mu dynamic. This is in a way relatively simple. We have a minus sign, worth noting, because we're looking at something opposing the velocity. It's slowing down the sliding motion. And then it basically just depends on the normal component of the force, how much the object is really pushing onto the surface. But right, this is fairly easy. The static friction is a bit less obvious on first sight, because what I gave you before was just this inequality for the force, and this is how you would actually compute it. Let me walk you through it quickly. So here we now distinguish. We basically have this minimum, meaning the static force that we really get is limited by a certain factor, and this is now related to the previous equation that I showed you. So here we have this mu static, or factor, and now we can see here that the force we're getting out of the static force is the minimum of two things, right? This and this. So if the inclination is not large, the object is resting, then the force is actually just minus the tangential one, which means the object is staying still. We're basically really canceling out all tangential acceleration that would cause any motion along the surface. Right? So if this is smaller than the second part, we're getting the full stop, the full cancellation. At some point, inclination, this will grow, and then we're switching to the other part, right? As soon as the tangential one is larger, and then we're only getting a part that actually depends on this material parameter. So in a way, that's also determining the limit. It's still scaled by the overall push on the surface, the normal force, but now it is actually acting along the tangential direction, which we now compute with this normalized tangential vector, right? So this part gives us the tangential direction by dividing by the magnitude of the tangential vector, and the first part gives us the magnitude this maximal force. However, in this case, then typically it will not be enough to keep the object from moving, and our box or so will start sliding down the inclined plane. So the idea is still the same as on the previous slide, but in equation form it looks a bit less intuitive. Right, and the first part is the one that I have it on slides, basically prevents motion, and then if I have this maximum as determined by mu static, then the object will start sliding. All right, so like mentioned before, this is the kind of correct viewpoint. However, we don't have forces. So what do we do instead? Well, again, an idea from the Millikan book is to actually adjust the impulses with tangential components to mimic this rubbing effect of the objects. Yeah, so what we can do is we can now apply a normal impulse along the normal direction, and then we can, in addition, look at the tangential component and basically tweak the impulse to take into account how the objects moved along this tangential plane relative to each other. So we still need to make sure that we fully get the normal part, right? The objects should not go into each other, they should get the right bounce back. But in addition, we can kind of align their relative motions along this tangential direction. And then, right, we might actually get a slightly different motion that's not just a pushback, but now has a certain component along the surface of the objects. So this tangential direction we can compute quite easily with, in a way, a double cross product. So you can try that out if you like, but we basically from the first part here we have the cross product between the relative velocity and the normal, which gives us a perpendicular vector, and then we're doing another cross product with the normal, which now basically gives us a perpendicular coordinate system where this vector is along the surface of the object we're interested in, and then we should normalize it to have a proper tangential vector. And for the impulse, we can now, in a way, simply change the way it's applied. So I only wrote the linear part here on the slides now. The angular part is directly in line with this. I don't think I need to write it out here. So this was the original part for the linear velocities, and now we're basically adding a friction part with some material parameter mu that now needs to encapsulate the material of both of these objects participating. And when applying the impulse, we are basically pushing it a bit along this tangential direction. Keep in mind the original impulse has opposing signs because the objects need to separate. This friction part goes in the same direction. This is not a typo, because also if the objects collide, they are actually seeing a certain joint influence here, and they really should move a bit in the same direction from this impulse. Yeah, so this is a simpler version of including friction effects in your rigid body simulations. Feel free to try this in the project exercise, for example. This can already give some interesting effects during the collisions. And so much for the contact and friction part.